The speaker today will be Nasila Mahmoudi from the Institute of Nuclear Physics in Lyon. Nasila is an expert in flavor physics and physics beyond the standard model. And as you know, the colloquium today is part of a series of colloquiums and talks dedicated to flavor physics. Last week we hosted a colloquium focusing more on the experimental side of the flavor anomalies. And today Nasila will present a theoretical review on the rare decays and search for new physics. So I leave you with the speaker. Thank you, Nasila.
Thank you very much. So first of all, can you hear me well?
Yes.
Okay, very good. So first of all, thank you very much for the very kind invitation. It's a great pleasure for me to be here and deliver this colloquium. So as was said, it's a continuation basically of what you have heard last week on the experimental part. So I will try to cover mainly the theoretical part of the story. And I will concentrate mainly on rare decays and search for new physics because this is where most of the activities in the field are going on. So in this colloquium, what I would like to cover is first of all an introduction to flavor physics, the part that we are interested in. So there's a big introduction, and I will start by defining what is flavor physics, what are flavor and what is flavor physics, and why is it interesting. There are, as I said, a lot of activities these days about flavor physics. There are a lot of nice features, a nice connection with new physics searches, and these are all very nice features. But whenever we talk about nice features, there is a but. So here also there is a but. The but is that it's very complicated. So I will describe why it is complicated and how we can deal with such a complicated story. And at the end, what we can learn from it. So this will be the first part of the talk, the introduction part. And then in the second part, I will describe mainly interesting decays in the context of search for new physics. So this will be rather brief. I will not describe in all the glory details, but just give you an idea of what are the main players, what are the main actors today when we talk about new physics searches and flavor. I will give you a status of what is going on currently, and then the implications for new physics. And at the end, there is a short part about future prospects, and I will finish by not really conclusions, but some final remarks. Okay, let's start. So actually, flavor is a very, very old notion in particle physics. So within the standard model, flavor is introduced by a triplication of the quark and lepton spectrum of one family. So basically, we take the gauge representation of the standard model and then we make 3 copies of it. So you all know that in the standard model, we have quarks and leptons, so this is the one family, and then basically we have 3 copies. We have a triplication of the gauge content. And so this is basically what we call flavor, is basically the different family that we have. We have 3 flavor families in the standard model. So you all know that we have 3 up-type quarks, we have 3 down-type quarks, we have 3 charged leptons, and then we have 3 neutrinos. So this basically gives us the content of the standard model. And flavor physics describes interactions that distinguish between fermion generations. So all the interactions between different fermion families, between different flavor families, is what is called, what is described by flavor physics. And then there are a few other definitions that you have already heard about them last week. So very briefly, you know that flavor mixings are parameterized by the Kobayashi, the Kebigo-Kobayashi. This is too well known. I'm too tired. So Kebigo-Kobayashi Maskeva or CKM matrix. So this you have seen in all details last week. Basically, it gives you the transitions, the mixing between different quarks. And we have also FCNC, flavor changing neutral currents, which was also introduced last week, I believe, which gives you the which concerns processes that involve either up-type quarks or down-type quarks, but not both. So you see between up-type quark and down-type quarks, the electric charge is different. So if you want the transition from up-type toward down-type, you need a charge current. So this is the charge current. And you cannot have a neutral current here. So a neutral current is only between up-type quark or down-type quark, and this is completely absent in the standard model. So we have no FCNCs in the standard model. And then another definition is the minimal Flavour violation, which tells you, or MFV, which tells you that the Flavour and CP symmetries are broken in new physics in the same way as in the standard model. So basically, we have the same structure, the same CKM structure and the same Yukawa structure as we have in the standard model. So this is the minimum Flavour violation hypothesis. Okay, now if we look at the parameters of the standard models, in the standard models we have 3 gauge couplings, we have 2 Higgs parameters, and then we have 6 quark masses, we have 3 quark mixing angles from one phase, this is what you saw last week, and then we have 3 lepton masses, and if you include neutrino masses in the standard model, then we have also 3 neutrino masses, and then in doing so we get a similar matrix also for the lepton sector, which is the PMNS matrix. So it's similar to the CKM matrix, which gives you the 3 lepton mixing angles and one phase. So actually, now looking at these parameters, you see that most of them are Flavour parameters. The masses depend on different parameters, on different flavors. The quark mixings and lepton mixings depend also on different flavors of fermions. So most of the parameters of the standard model are Flavour parameters. So it's actually a significant part of the standard model. It's basically the heart of the standard model. So it's very important when we want to complete or understand or study standard model, we have to understand Flavour physics. Okay, so now why Flavour physics is so interesting? There are many reasons for that. First of all, CP violation is very closely related to Flavour physics. It's a topic of Flavour physics. So we know that the only CP violating parameter in the standard model is the CKM phase. So, however, we know from baryogenesis and from particle-antiparticle asymmetry in the universe that this is not enough actually to explain, this is not enough for cosmology. So this is something very important both for particle physics and for cosmology. We need to understand what are the new sources of CP violation, because what we have in the standard model is not enough to explain all the phenomena. So that is a very important topic. Also, there are some very fundamental and basic questions in the standard model which are about Flavour physics. We have what is called the standard model Flavour puzzle. And here the question is that we don't understand why Flavour parameters are small and also why they are hierarchical. So if you remember from the CKM matrix from last week, you see that the elements are hierarchical. And also the masses of the fermions are hierarchical. So we don't understand what is the fundamental reason behind this structure in the Flavour parameter. So this is the standard model Flavour puzzle. And similarly for new physics also we have new physics Flavour puzzles. And basically, as I told you, Flavour changing neutral currents in the standard model are absent, and we don't understand why they should be also absent in new physics. Why new physics should have exactly the same structure. If you assume that new physics is at the TeV scale, then why all Flavour changing neutral currents are so small, are so negligible? Because if new physics had a generic Flavour structure, then it should also contribute to FCNC processes, which is not the case. So these are very important and fundamental questions that are completely related to understanding of Flavour physics. And there's another reason which is extremely important these days, is the fact that Flavour physics is sensitive to new physics at the scales that can be much, much higher than the scale that can be available experimentally. So if we want to understand or study new physics, if we want to discover new particles, what we should do, the first thing that's coming into our mind is that, well, to build an accelerator, accelerate particles and try to generate the new particles directly. So trying to do a direct discovery of new particles. But for that, we need to know what are the masses of the new particles in order to know what should be the energy of the experiment. So if we don't know what is the mass of the experiment, we can just try, and then depending of if the mass should be at the order of 100 GeV or TeV or tens of TeV, then you need a different accelerator. This is very costly and extremely difficult. On the other hand, new particles can also appear in the intermediate state, not only in the final state in a process, but they can also be in the visual state. And so, even without producing them directly, even without having that much energy, or knowing what is the energy to produce them directly, we can probe them by studying them in the processes where they appear in the visual states. And this is exactly the case in decays, in Flavour physics in general. So that means that we don't even need to produce them directly. We can already study getting an insight about the order of the masses and the properties by just studying Flavour physics processes. And this is very interesting. And it can, on one part, it can help us, maybe even, it can maybe lead to even discoveries, or it can guide the researchers, and we can use the complementary aspects of the two. So this is very important. Okay, so what do we know so far? So we know that all present measurements of Flavour observables are consistent with the CKM mechanism. And this is an impressive success of the standard model and the CKM framework that you have seen last week. We know that the CKM phase is different from zero, so we have this CP violation in the standard model, so this is confirmed, even though it's not sufficient, but we have observed it. We know that the CKM mechanism is the dominant source of CP violation, which is observed in the meson decays. And also, well, there are still some studies ongoing, and CP violation in some decays may still hold some surprises. So this is something actively ongoing and being studied. And also, we know that new physics contributions to the observed Flavour changing neutral currents are at most comparable to the CKM contributions, because otherwise we would have observed them. So, okay, these are all the things that we know. And now, there has been somehow a change of objective in the field in the last few years. For a long time, the experimental objective were mostly focused on the test of the standard model, test of the unitarity, triangle, and measuring precisely the CKM elements. This is, of course, of great interest, and it's still ongoing. But the focus now is mainly toward new physics and search for indirect signs of new physics. Sometimes it's even easier to see something first indirectly and then directly, and the prime example for this is the roundness of the Earth. You know, it was discovered indirectly 2,000 years, more than 2,000 years before we could observe directly the Earth by satellite and see that it's actually, and see the roundness of the Earth. So I hope that we will not have to wait 2,000 years now to discover new physics, but it's of great interest. And the good point is that there are many Flavour observables under investigation, so the situation is really promising. We have a great laboratory. Okay, now, why is complicated? Well, it's complicated mainly because two reasons. Here, the problem is that we have a mixture of strong and weak interactions, and we have to deal with this complicated system. In one hand, we have weak Lagrangian in terms of quarks, but the final state is hadronic, so this is something very complicated system. And also, we have many different scales involved in the calculations. So we have the light quark masses, for example. We have lambda QCD, we have MB and MC, and then we have MW, which is suddenly much larger, and then even the scale of new physics, which can be much larger. So we have to deal with a very different set of scales at the same time, and that's why it makes the calculation very difficult. But if you look at the scale of P physics, it's basically below MB. It's MB or below. And looking at this, we can just ask, so then why not integrating out all the heavier degrees of freedom and keeping only the light quarks B, C, S, and D, U, and also Q1 and photon as dynamical particles. And this is a way to deal with this in order to simplify the solution, the problem exactly. So this is what is done in the effective field theory approach. the idea here is to separate between high energy and low energy parts using operator product expansion. Let me explain this with a simple example. This is probably the simplest example that we can imagine. So here we have this diagram B transition of P to C and then C to S with the exchange of a W boson here. And we can write down the amplitude for this diagram rather easily in the full theory, in the complete theory. So basically you write down the Feynman rules for this Feynman diagram, and then you write down the amplitude. You see in the amplitude we have these CK matrix elements of these transitions. We have the two currents here, and then we have the W propagator. So usually this K, the momentum of W is much smaller than the mass, and so we can make an expansion here, and so here we get 1 plus order K square R and W square collections. So okay, this is what we can do in full theory, but now we can do what we just said. So we can just remove the W boson here, and remove it as an explicit degree of freedom, and then consider a generic type of diagram, an effective diagram like this, where we don't care about what is going on here. We are only interested in the two currents that we have here, which is called O here. And then to calculate this, of course, we have to have a coefficient here, which gives us all the other things which are going on. And so the amplitude, I can write it like this. I can have a set of O operators times the coefficient, and then we have, of course, the CK elements, which gives us the transitions. So actually, in this way, we separate the long distance and short distance parts. So the long distance parts are given in these operators, for like this one, for example, and the short distance part of the theory is embedded in this C coefficient, which are called the Wilson coefficients. And basically, we can obtain these Wilson coefficients by doing a matching between the two. So at the end, the two methods should give the same results. So we can do a matching of the two, and then by just comparing the two, you see that in this particular case, the C coefficient here is simply equal to 1. It can be much more complicated in some other cases. But by doing this matching, we can obtain the Wilson coefficient. Okay, this is a very simple example. In reality, what we have always is the exchange of gluons everywhere, and we have to calculate the higher orders, and it's more complicated, but anyway, it's the method works like this even at higher orders. So at the end, we have an effective Hamiltonian, which is given like here. We have a set of operators times the corresponding Wilson coefficient, and then the CK matrix elements. And if you look at the B12 transitions, these are the main operators. So we have, for example, the so-called 4-quark operators. We have electromagnetic dipole operator, where you have the emission of a photon. And then you have a gluon emitted, and this is the chromomagnetic dipole operator. And then we can also have the semi-electronic operators. So here we have a pair of leptons in the final state. So these are the diagrams in the full theory, and we can look at the equivalent in the effective theory. So these are the 4-quark operators, for example, and then electromagnetic operator, which is O7, chromomagnetic operator, which is O8, and then the semi-electronic ones, which are O9 and O10. So here, if you look at the structure of the operators, we can also flip the chirality of the operators between left and right-handed, for example, and then this gives us the so-called prime operator. So we call them with a prime if the chirality is flipped. Okay, well, so now you may wonder why there are penguins everywhere in my diagrams, because these diagrams are called penguin diagrams, and I will be dealing with penguin diagrams everywhere. But then, why calling this a penguin diagram? Do you think it looks like a penguin? It requires a little bit of imagination, but if you try hard, you may see this. So that's why they are called penguins. But no. There's a story saying that once Feynman was asked why these diagrams are called penguin diagrams. They don't look penguin like penguin. And Feynman replies, well, you know, Feynman diagrams don't like me either. Well, okay. If you ask the same question from John Ellis, who named this diagram penguin diagrams, he will tell you that depending on what you have smoked, you may actually see a penguin. Okay, anyways. So, now we have identified the structures of the processes. We know that we need Wilson coefficients and operators, and so now we have to calculate the Wilson coefficients. And the Wilson coefficients, as I described, the main step to calculate that is just doing this matching at MW scale between the full and effective theory, and then this we do it at order by order. So I showed you an example at tree level, but then at each order we do this matching separately. And by doing this matching, we obtain them at each order. But this is done at the matching scale, which is typically the MW. We need, on the other hand, the scale which is relevant for B physics is the B, the B quark mass scale. And so we need to obtain this Wilson coefficient at a lower scale, and this is what is usually done by renormalization group equation. So every time you know something at one scale, you want to obtain it at another scale, you use renormalization group equation to evolve them at the scale that you want. So this is exactly what is done here. There are different ingredients that you have to calculate, but the point that I want to make here is that the standard model contributions of the Wilson coefficients are known to a very, very good accuracy. So the progress here was really impressive, and here, this is the nice part of the story. So this is the beautiful part. Everything is clean, we can calculate, and it's done with a lot of effort. So this is everything. Here, everything is fine. And just to give you an idea, C7, for example, in the standard model is about minus 0.3, C9 is about 4, and C10 is about minus 4. Okay, good for that. We have the Wilson coefficients, but now we have to calculate the amplitudes. And to calculate the amplitudes, we need the effective Hamiltonian. So if you insert the effective Hamiltonian here, you see we have the Wilson coefficient, but we also have these matrix elements of these operators. So we have to calculate these hadronic matrix elements. And this is where things are a little bit less clean or less nice, because it's very complicated. And so we don't have as precise results as we have for the Wilson coefficient. So how to do that, how to calculate the matrix elements, basically it requires a lot of model building. It's complicated, so we use usually lattice simulation to do that. And again, because it's complicated, we try to use all the symmetry properties of that we have at hand, light Flavour symmetries, heavy Flavour symmetries, etc. And then at the end of the day, we describe the hadronic matrix element in terms of what's called hadronic quantities. And there are two types of hadronic quantities, which are the decay constant and form factors. Okay, let me describe them briefly. So the decay constant first gives you basically the probability amplitude of hadronizing a quark pair into a given hadron. So here, for example, if you write down the matrix element corresponding to this, this is what we have, the hadronization of 2 to a B. I mean, from 0 you go to a B hadron. And this matrix element, we can call it Fp. So we just name it Fp. And we know that here we have one Lorentz structure, which is the momentum P mu, or the moment of the hadron. And so we call it something like this, P mu times Fp. And Fp, this is what we call the decay constant. And so, okay, here now we have to calculate it. And then it's complicated. The second hadronic quantity that I talked about is form factor. So the form factors give us the transition from one meson to another through Flavour change. So here, for example, we have a transition of B to a pi meson with the exchange of the W boson. So here, if I write down the matrix element, I can use again the available Lorentz structure. So here I have two momentums of the B and the pi mesons. And so I can build all the Lorentz structure that I can, so that is P plus P prime mu and P minus P prime mu, and multiplied by these form factors this time. And now again we name them form factors, we have to calculate them. This is a simple example, just one meson transition. It's more complicated if you have more mesons, and it's also more complicated if you have vector mesons, because then you have also polarizations and you have more form factors. So at the end, these form factors, we calculate them either, as I said, using lattice results, etc., or we can also try to deduce them experimentally. If there is a decay that is well measured, then we can use it to extract the form factors. Okay, so just to recap, we start with a very complicated problem. We have strong interactions in non-perturbative regime. You see, in reality, if you look at, for example, B to D pi transition, in reality, that's how it looks like. You have a gluon exchange everywhere, and the system is really complicated. And the starting point to deal with is just define an effective Hamiltonian. To do that, we have to follow 3 steps. First, by matching of the full theory and effective theory at the W mass scale, we extract the Wilson coefficients, and then we evolve the Wilson coefficients using renormalization group equations to get them at the B mass scale. And then we have to calculate the matrix elements, which require the calculations of the hadronic quantities. So this is the procedure to follow. And now why this effective approach is advantageous? It's because it allows us to simplify this complicated system that I showed you by keeping only the relevant degrees of freedom. So we are just interested in the particles of interest for the P system and the relevant degrees of freedom. And it's also interesting because it can be applied to any processes. So it's a generic framework which can be applied everywhere. And when you consider new physics in addition, the extension is rather straightforward. But basically, you use exactly the same framework, and so it's very interesting. All we have to do is to calculate the new physics contributions to the Wilson coefficients. Good for us, the Wilson coefficients are additive. So we just consider the new diagrams, and then you do the matching again in the same way as in the standard model, and we obtain the new contributions. Or sometimes we can have new operators that are absent in the standard model. And in this case, again, you add a term, including the new operators times their coefficient in the effective Hamiltonian. So basically, you use the same framework, and it's very straightforward. And another interest of this method is that many observables share the same Wilson coefficient. Basically, once you have calculated the Wilson coefficients, you have it for all. So you suffer only once, and then you have it, and you can use it in all the processes involving that topology. So it's interesting also for this. Okay, with this, let's move to rare B decays. So rare B decays are very interesting because they occur at loop level. Here we are talking mainly about FCNCs, Flavour changing neutral currents. You see, they are absent at tree level. We don't have any neutral current at tree level, and so they occur only at loop level. And because of this, the standard model contributions are very small. And this is actually a good point, because then the new physics contributions can have a comparable magnitude. And so you can compare two things which have comparable magnitude. Imagine if you have a huge new physics contribution and you want to find the huge standard model contribution, and you want to find the tiny new physics contribution in it, so it will be very complicated. Here, for the loop decay, it's not the case, so this is very good. And also, a good point is that there have been so many efforts in the theory community, so all the theory ingredients are known at a very, very good accuracy. The calculations are very involved, and so in particular, the QCD corrections are known with a very good precision. And also, the experimental situation is very, very promising. There are many ongoing measurements, and the future prospect is also really nice because there are more and more results coming from LHC, and also there will be more results coming from BED2 very soon. And so it's a very interesting situation also from the experimental point of view. So all in all, rare B decays are really ideal choices to look for indirect signs of new physics. So let's have a very brief look at the most sensitive decays in terms of new physics. So here, let's start by the famous decay of B. to S and gamma. So here I'm talking about an inclusive decay. So I just care about the B quark transiting to S quark and emitting a photon. Here, this is an FCNC, and so it appears only at loop level. Here are some examples of the involved diagrams. And so the main operator for B to S gamma decay is the chromomagnetic operator 07. And you can see in the loops we can have different ingredients. We can have the standard model contribution with the exchange of a W boson, and then you can have a photon emitted somewhere. But then we can have in the loop contributions from new physics scenarios, from an extended Higgs sector, for example. Here is a charge Higgs, or we can have supersymmetric contributions, or whatever you wish. And so you see these are all loop diagrams, and so we can calculate them, and by comparing to the experimental results, we can obtain some constraints. I should mention that P to S gamma was the first penguin ever observed. If I'm not wrong, it must be in 93 by Clio. And so now you can see the experimental average from different experiments for the branching ratio of P to S gamma, which is at the order of 3 10 to minus 4. Okay, so now we can calculate this branching ratio and compare with the experimental value. And this is really scary. So if you want to have a precise calculation, we have to calculate all the high order corrections when you have gluons emitted and exchanged from everywhere. And you see you end up with having this sort of complicated diagrams that if you want to have enough precision, or to be at, for example, next to next reading order precision, then you have to calculate the 3-loop matchings, and it's a lot of diagrams. So basically, you have something of the order of 10,000 diagrams like this to calculate. But then, once this is done, it's rewarding, because then we have a very stable and precise result. So here I'm showing you the scale dependence of the branching ratio. This is a mu W and a mu V scale. And these are different orders of calculation. So this is the first order of calculation, or leading order. And this is when you add some high order calculations, so next reading order. And this is when you add even more high order calculations, so more loops. So what you see is that you see the branching ratio when you're at the leading order, at the first order. The branching ratio varies a lot with the scale. And this is something on Física, so the branching ratio should not depend on the scale. If you do a perfect calculation, you should be completely independent of the scale. You see, this is not the case. If you go to next leading order, the scale dependence becomes less. And if you go to next leading order, so when you calculate all these scale diagrams, then you see you have basically no scale dependence. So it shows you how the results are stable and precise. It's very similar also for mu V dependence. So at the end, the standard model prediction is very precise, and it's very similar to the experimental results. So the experimental average was 3.32. The SM prediction is 3.34, 10 to minus 4. So they are very, very close. And that's exactly why this decay is so constraining for new physics, because you have almost no room for any new physics contribution. So it gives very strong constraints and new physics contributions to C7 in particular. Okay, another decay of interest in terms of searching indirect effects of new physics is PS decaying PS meson, which include the B and S quark, decaying to a pair of muons, mu plus mu minus. So again, this is a loop level diagram. We can have this sort of penguins, and we can have also box diagrams in the standard model. And again, in the loops, you can have, in addition to the standard model particles, you can also have new physics particles, similar to what we have for C7. Here, the main operators are this semi-electronic operator, O10, and also we have this scalar and pseudo-scalar operators. So you see this is the structure is a scalar operator, and here is a pseudo-scalar operator, which are absent in the standard model. So this is an example where you have to add new operators in the effective Hamiltonian. And so the branching ratio of this decay can be written in terms of the Wilson coefficients, so CS, CP, and C10, the Wilson coefficients of these operators, and it depends also on the decay constant of a BS. And so this decay constant, as I said, the hadronic parameters quantities are where things are a little bit less keen. So this is where we have some uncertainties coming to the game. Okay, and you can compare the experimental measurement. I should say that this was actually BS to mu mu was for a long time waited to be measured, and we finally had the first measurement at LHC by LHCb and CMS experiments. And the combination, it was in 2013, if I'm not wrong. Before we only had limits from Tevatron, mainly. So, okay, the combination of the branching ratio is 3.1 10 to minus 9, the experimental branching ratio. So it's very small, it's very rare. And you can compare it with the standard model prediction, which is very similar. So a little bit larger, but compatible. So the standard model prediction is 3.4 10 to minus 9. Now, why this decay is so interesting and attracted so much attention, it's because it's very sensitive to new physics contributions, in particular in the MSSM, in supersymmetry. So in supersymmetry, these diagrams, just generically speaking, are something like this. And if you calculate this, you see that it goes like tangent beta to the 6, which is one of the parameters of supersymmetry. And so it's very sensitive to these supersymmetry parameters, to tangent beta. And in principle, you could expect orders of magnitude enhancement as compared to the standard model. So that's why people were so much waiting for this measurement. Because if the measurement, imagine, would have been 10 times the standard model predictions, then that would have been a nice, a hint for the existence of new contributions. Unfortunately, as you have seen, the experimental result is very similar to the standard model prediction. So these large contributions are now ruled out. Okay, another decay of interest is a decay of a B meson to a K star and a pair of leptons. So here we have a rather complicated system because you see the B decays to a K star, but the K star decays itself to a K and a pion. Let's say it's a complicated geometry, but on the other hand, it's very interesting because it gives access to many different angular observables and many different, let's say, experimentally measurable quantities. And so it's very interesting. So what we can do is to describe basically all the decay distribution in terms of these these three angles that we have in this plane, and also the Q squared, which is the dielectron invariance mass squared. So we have 4 kinematic variables, and we can write down the differential decay distribution in terms of these 4 parameters. Then what we can do is just to separate the angular part from the Q squared dependent part. This is what is given here. So we have these J functions, which are the angular coefficients, and we have this angular function. And the way we do the calculation is that these J functions are functions of the amplitudes, the spin amplitudes, and the amplitudes are functions of Wilson coefficients and form factors. The formulas are rather lengthy. I didn't put them here. I just tell you in board. So at the end, it's the same story. You have to calculate the Wilson coefficients and the form factors to get the amplitudes and to get these J functions and to get the decay bit. And here, the relevant operators are, the semi-leptonic operators, O9 and O10, and we can also have contributions from the scalar and pseudo-scalar operators. So what we can do is integrating out these over the 3 angles, and then you get the decay, the differential decay bit. But then there is a problem is that you have a large uncertainty coming from the form factors. So here, for example, there are 7 form factors involved, and the branching ratio has a very large uncertainty. So as I told you, in order to look for new physics, we need something which is precise and which is well known, because otherwise you cannot distinguish new physics effect from your uncertainties. And so here the branching ratio is not a good observable. And that's why there have been a lot of effort in the community, in the theory community, to build clean observables. Kim Matthias is one of the pioneers who is in the room. to do this sort of efforts in order to provide observables which are less dependent on the form factors, on the hadronic uncertainties. And this is a set of observables which are called the so-called optimized observables, P1, etc., which are, in brief, they are combination of different spin amplitudes built in a way to eliminate the uncertainty from the form factors, at least at tree level. And these are quantities which are experimentally measurable. And so the idea is just to measure these observables and see if we can see any hints of new physics in these observables. Okay, another one which is not really a rare decay, but I nevertheless put it here because it's very sensitive to new physics, is the P to tau nu. So this time it's a tree-level diagram. That's why I'm saying it's not a rare decay, but it's interesting nevertheless because it's at tree level. It's mediated by a W boson that you can replace by some new particles in new scenarios. For example, by charges in scenarios with extended Higgs sector or in supersymmetry. And so these two, what happens is that in the standard model, this decay is helicity suppressed, while you don't have this suppression in with the charging, and so these two decays can have a comparable magnitude, even though they are tree-level decay. And if you write down the branching ratio, basically one corresponds to the standard model, and then you have the new contributions from the other diagram. And here you see there is this FB appearing, the decay constant of P to tau nu, and so this is a large. This provides a large uncertainty. And in addition, BUB has also some large uncertainty. But this is very interesting again, and so you can compare the standard model prediction, which is 1.4 10 to minus 4 to the experimental average, which is about 1.1 10 to minus 4. And this can give some strong constraints. There are similar processes to this that I didn't draw because they are very similar. For example, B to D tau nu, so it's the same with the spectator part. Or you can have D or DS meson decaying to a lepton and a neutrino, to a charged lepton and a neutrino, or similarly a K meson decaying to a mu and mu, for example, here. So these decays, theoretically speaking, were more or less similar, but some are more complicated. This one is a semi-leptonic decay, is a little bit more involved, but they are all interesting also in the search for new physics. Okay, now let's move to the observables and the anomalies. So the observables which show some hints for new physics or some tensions, let's say, in the first place with the standard model. How am I doing in time? 20 minutes, okay, very good. So there have been a lot of efforts in the past few years, mainly at LHCb experiments in order to measure B to S transitions with a pair of leptons. There have been so many different measurements in different decays, a lot of efforts. And in these measurements, some of them have shown some deviations with the standard model predictions. So these are what we call the anomalies, but they are not really anomalies, and strictly speaking, they are just deviations with the standard model predictions. But nowadays, in the jargon, we call them anomalies. So here are these a summary of some of these anomalies. So you can see, for example, here is the decay of P to AK and a pair of lepton. So you see the experimental measurements in the black process and the standard model predictions in the band. You see here that the experimental measurements are below the SM prediction. Similarly, this is for a K plus. Similarly, for B0 to a K0, again you see that the experimental results are below the SM predictions. This is for a B to K star. Here you see again, these are all branching ratios. You see again that the experimental results are below. For BS to 5 mu decays, they are again below. And even for lambda B decay to lambda mu mu, so this is completely different. Again, you see that the results are, the experimental results are below the standard model predictions. So all these deviations with the standard models are between 1 and 3.5 sigma. And there is an interesting common feature that you can see is that it seems that in all of them, the experimental result is below the standard model predictions in the small Q-squared regions. So it shows us somehow a coherent pattern, but on the other hand, they are all branching ratios, and we discussed that the branching ratios have very large uncertainties from hadronic quantities. So you can see in the plot also the uncertainty from the width of the bands corresponds to the uncertainty of the prediction. Okay, there have been another measurement, more exciting, which is not the branching ratio. So this time, this is the one of these optimized observables, the so-called P5 prime, which is also called S5. There's a small, slight difference in the definition, but they are similar. So these measurements came out in 2013 with the first inverse femtobarn of data of LHCb, and you see the result here. In this particular bin, you see this deviation with the deviation of the experimental measurement with the standard model prediction, which is at the order of 3.7 sigma. So okay, that was very exciting, but at that time we need confirmation from the experiment, etc. It could be a statistical fluctuation. So the next result came out in 2015 with the 3 inverse femtobarn of data, and you see that the deviations are still there. So here the binning is refined, so we have more measurements here, and again you see that the experimental results are above the predictions. But then there was another analysis with the same data, but using a different analysis method, and also a more refined binning, and you see that the deviations are still there actually. So with more data and with more refining analysis, we still have at the order of 3 sigma deviation with the standard model. So at some point we cannot speak about statistical fluctuation anymore. And then there was a measurement also by from Bell, which you can see here, which supports, you see it's again above the standard model predictions in this field, which supports then the LHCb result, but the errors are much larger here. And if we look at the current picture, this is the current results for P5 prime, and you see we still have these deviations here. So it was also measured by ATLAS and CMS, but with larger uncertainties. So the deviations are still here, and I guess now it's really difficult to think of statistical fluctuations to explain these deviations. We have this deviation also in BS, going to a phi meson and a pair of lepton in the branching ratio. So this decay is very similar to B2K star mu mu. The form factors are just different. And it was measured in 2015 with 3 inverse femtobarn of data at LHCb. And you see the experimental results that you can compare with the SM prediction, and you have a deviation at the order of 3 sigma also here. Then we have a very interesting measurement trying to test lepton flavor universality. So here, the idea is to consider B to K, decay of B to K mu mu. It's very similar to B to K star. The only difference is that the K is a scalar, so the calculation is a little bit different. But what is interesting here is to consider the ratio of decay of P to K to K and a pair of muon over the same decay with electrons in the final state. So this is the so-called RK ratio, and it's very interesting because since it's a ratio, it's very, very clean. You see the standard model prediction is extremely precise. And so here, really there is no problem with any theoretical uncertainties. And we can compare with the experimental results, which came out in 2014 with using 3 inverse femtobarn of data. And you see that it's very below 1. So the SM prediction is basically 1. And here there is a 2.6 sigma difference with the standard model. So this is something very interesting because in the standard model, lepton flavor is universal. So if we discover some non-universality of lepton flavor, we discover some deviation from 1 here, then this is something which is absolutely not explainable with the standard model. So you need really new physics. So that could really be a breakdown of the standard model. There was another measurement in April 2017 for a similar ratio, but this time with a K star. So you look at the ratio of B going to a K star and a pair of leptons over B going to a K star and a pair of electrons. And this measurement is done in these two Q-squared bins. And again, you see the difference with the standard model predictions. And okay, now I realize that I forgot to put the standard model values, which are also close to 1. Sorry about that. But okay, in any case, you can see it here. Yes, so these are well below 1. The standard model is close to 1 for the first bin and almost 1 for the second bin. And it corresponds to the tension of around 2.2, 2.5 sigma with the standard model prediction in each bin. So it supports basically the same sort of results that we have for RK. Okay, now how we can make sense of this data, what we can learn from these deviations. So the way to interpret these so-called anomalies is we can take two approaches. We can either consider a model-independent analysis where we want to have some generic information about the involved Wilson coefficients, or we can do some sort of model-dependent analysis where we want to study the model-specific properties, the mediators, the UV complete models, etc., etc. So both approaches are possible and required. So in order to do a model-independent analysis, we just want to know what are the contributions to the Wilson coefficients. And for that, we can do global fits of all the available data and see what global fits to all the data tells us about new contributions to the Wilson coefficients. How am I doing in time? 10 minutes, okay. So to do that, we do scans over the Wilson coefficients. Basically, you choose randomly different values for the new physical contribution, and with these Wilson coefficients, you calculate the Flavour observables, compare with the experimental results, and in this way, we obtain constraints on the Wilson coefficients. And here, of course, we have to be very careful about theoretical uncertainties and correlations between different parameters, etc., etc. So we have to take care of all these errors and correlations and calculate a theoretical plus experimental correlation matrix, which can be used to calculate the chi-square, which then we have to minimize in order to find the favored region for the different Wilson coefficients. So for that, we use all the available data from the different decays that have been measured. And here, let me just show you the results. So if I do the fit, allowing new physics contributions to one Wilson coefficient, let's say C9, for example, here, then I can find what value of C9 fits best the whole data. And then I obtain the best fit value. And then I can also find what is the minimum chi-square and what is the tension with the standard model. So this is maybe the last number is the one which is more interesting for us. So if you allow new physics contributions to C9, you see that we obtain 4.3 sigma pool with the standard model. So basically you get a 4.3 sigma improvement in the description of the data as compared to the standard model. Similarly, if you allow for with new physics in the C9, but only in the muon part, you remember these operators have pairs of leptons, so you can consider separately for muons and for electrons. And so if you consider only the muon part, then we get an improvement of 4.5 sigma compared to the standard model predictions. So this is including all the observables except RK and RK star, giving some, considering some theoretical uncertainties for the hadronic parts that we don't know, and this is what we obtain. And now we can look at the fit results, global fit results, if you consider only the data from RK and RK star. And you see that, again, we can explain the data much better than the standard model if we consider new physics in C9 muon part, in C9 electron part, and also this time we have some solutions also for C10 muon part and C10 electron part. So we have an improvement of the description at the level of 4 sigma. And this is also confirmed if you consider the same fit, but this time new physics contributions to 2 Wilson coefficients, not only 1. 2 can receive new physics contributions at the same time. Since my time is short, I will not go to the detail, just saying that it gives you the same results. So it tells you that you need new physics contributions in C9 and in particular in the C9 muonic part. So the outcome of the model independent analysis is that in order to explain the anomalies, you need new physics in C9 Wilson coefficient at the level of 25% deviation. So basically decrease in C9. And with this, we can explain consistently all the anomalies that I mentioned before. The fact that we have a consistent explanation possible for all these anomalies is really attractive. So they all go in the same direction and follow the same pattern. Okay, how to resolve the issue, how to understand if this is really new physics contributions? Well, first of all, we have to improve on our precision of the theoretical calculations. So there are still some ingredients, some QCD ingredients which are unknown or which are partially known. So we need to think better and come up with new methods and alternative approaches in order to really improve on this precision as much as we can. And there are several elements already, and there are works ongoing. So here the situation is good. We can also do cross-check with other R ratios. So I told you about RK and RK star, but we can consider ratios of other decays or other observables and see if they are consistent with what we have now or not. We can make predictions for them, and then if they are measured and they are consistent with our predictions, then that would be a confirmation, a new physics confirmation for these anomalies. So some of them are very interesting. For example, if you consider the ratio of P5 prime, so P5 prime for muons and P5 prime for electrons, and you get the ratios, then we can have some interesting cross-check to do. Okay, another way is to just wait for LHCb future results, because here we can actually, LHCb will have enough statistics and enough precision to really tell us if this is a new physics contribution or not. This is an example of a projection for LHCb in the plane C9 mu and the C9e. So the red contour is the 2 sigma favored contour now, which is away from the standard model, which is here at 0. And then if you consider projections with more data of LHCb, you get these green, blue, and yellow contours. And so you see you get so much power from the standard model, which is here, that at some point it's unambiguously new physics. So if we just wait for LHCb data, then I guess the situation will clear up if the deviations still remain, of course. Okay. And then another possible cross-check is a cross-check with inclusive modes. So in the inclusive modes, we just don't care about the we just take care about the quark transitions, not the whole meson. So we are not considering the meson or hadronic system, so there is no hadronic uncertainties. So these are well cleaner than the exclusive observables. And what is interesting is that Bell 2 will soon start measurements of these inclusive observables, and then by cross-checking the results that we have now from inclusive measurements, from exclusive data from LHCb, and the inclusive measurements, we can again check the compatibility between the two and see if they are coherent or not. So this is an example of the fit results of the exclusive measurements that you can compare with prospect, for example, experimental measurements and the standard model predictions, which is here, and see if in the future they are compatible or not, and they hint toward new physics or not. This is another interesting cross-check to do. So now in the last few minutes that I have, I will describe the other approach, which is considering this time model dependence. So see which sort of models can explain the anomalies. So what we have learned from model independent analysis is that we need new physics contributions to C9. So this is what all the things are telling us. Also C10 can be changed a little bit, but in a lesser extent as you have seen. So basically what we need is to generate xenon, delta xenon equals to -1, 25% change in xenon at loop level. I mean, this is completely, it's very, very difficult to do because loop corrections are very small compared to the normal corrections, and so at loop level, it will be very, very difficult to get. So, for example, in the MSSM, it's very difficult to get this because all the MSSM contributions to xenon are at loop level, and so, I mean, you can go to very specific regions of the parameters, but generically speaking, this is very difficult to obtain. So let me just go to other scenarios. So if this is complicated to obtain at tree level, then we can think of, at the loop level, sorry, then we can think of a loop, I'm sorry. Then we can think of tree-level generation of xenon. So the mainstream scenarios to generate xenon at tree level are scenarios including a new boson, a new Z boson, which is called Z prime, or leptoquarks, or composite models. So very briefly, what these scenarios are. So a very easy to generate xenon is actually including a new Z boson, a Z prime boson here at tree level, which can give enough contributions to xenon as we were hoping for. So here, what we need is a flavor changing coupling to left-hand quarks for this vertex, and a vector-like couplings here to leptons, and we need flavor violation or a non-universality in the lepton sector in order to explain RK and RK star. So this is rather easy to do, but we have to be very careful because there are strong constraints, in particular from BS bar mixing. You see this vertex is exactly the same as what we have in BS and BS bar, and so when you want to mix BS and BS bar mixing, BS and BS bar, you get strong constraints here. And also from LEP, because at LEP, so the previous experiment at CERN, which was electron-positron accelerator, so we have E plus E minus going a pair of muon, that was very precisely measured, and so we have constraints also from LEP on this vertex. But nevertheless, it's possible to build models with a Z prime of about of a mass about 1 to 10 TeV to explain the anomalies, and then one can also think of incorporating this Z prime in more evolved or more realistic models. Another possibility is with leptoquarks. So what are leptoquarks? Leptoquarks are objects which carry both lepton and quark quantum numbers. And so they can couple to both quarks and leptons. And this gives you this sort of axis, because it can couple to both lepton and quark, and so we can have a T-channel diagrams like this. And so we can think of different representations of vector quarks. It can be a scalar or a vector. But then here the point is that this leptoquark can give contributions to C9 with this diagram, but it gives also contributions to C10. So it changes both, not only C0. And then usually if you have this sort of diagram, we want to have flavor non-universality to explain RK and RK star, but then you get also diagrams like the lepton number can also be violated. So you get diagrams like this one, B going to S plus muon and electron. So you see the lepton number is violated here, or mu going to E gamma. So these diagrams are also possible in such scenarios, and we have to be careful about. A way to circumvent this problem is consider two leptoquarks coupling to one lepton type only each time. And then there is another mainstream scenario, which is with composite models. So here there is a lot of activities independent of flavor anomalies in this sector. Basically, the idea is that to say that we don't know if all the particles that we think are fundamental are really fundamental. Higgs boson, for example, can be a composite particle, and then there are a lot of work done. And these sort of scenarios can also be used to explain flavor anomalies. So here, for example, we can have a new boson rho mu, which can couple to muons and to B and S, but here you have to consider some compositeness for the muons, for example, and you have to allow for lepton flavor violating couplings, and so you can again generate a C9 at 3 levels with this sort of diagram. But here again, we have constraints from lab measurements and also from BS to BS bar mixing. It's a complicated system because it's non-perturbative and making predictions is more difficult, but there are nevertheless a lot of studies going on here. Okay, so I'm coming to the end. At the end of the day, what we want to do is to cook a nice scenario. Very elaborated, very tasty, very complicated. So in order to get to this nice endpoint scenario, we need to know the ingredients that we have to use. So this is what we do with the model-independent approach. The model-independent approach gives us the ingredient that we need in order to cook our model. For example, what we have learned from the anomalies is that we need C9 as an ingredient. We need maybe a little bit of C10, etc. So this gives us the ingredient. This is the first step and it's important. But of course, it doesn't give you the dish that you expect at the end of the day. So what we should do is just to try to cook up something simple first in order to learn. So this is what we do with a simplified model. So basically, you put your ingredient together and then you cook up something simple. But this is not the whole story. This is not what you want to have. So what we want to have is this pattern. And so for this, we need really a complete scenario, and this is quite a whole complicated work, and we are not there yet. So we are at the moment in this level. So, but the main idea is to cook this nice dish at the end of the day. Okay, so let me just move to my final comments. We have seen all these anomalies, and of course it's a very hot topic these days in flavor physics and in particle physics in general. And so how to explain this? What is the situation today? Can we explain the anomalies by just statistical fluctuations? And the answer is no, because you have seen these anomalies in so many different decays with more and more experimental measurements with different analyses. It cannot, statistical fluctuation alone cannot explain all the observations that we have today. So this is clearly no. Can this be, the anomalies be some experimental issues? Some problem in the measurement, some error in the trigger, or whatever you can imagine? And again, the answer is no, it cannot, because we are talking about so many different decays, completely different processes. So one same error cannot explain everything that we are seeing in all these different decays. So this is also no. Can the anomaly be explained by underestimated theoretical uncertainties? And again, the answer is no, because some of these observables are extremely clean, like RK. There is no theoretical uncertainty, so there is no way to explain RK with theoretical uncertainty. So the theoretical uncertainty alone cannot explain all the anomalies that we are seeing. Could this be because of unknown pieces in the theoretical calculations? The answer is again no, because as I said, some of them don't depend on these ingredients. But combination of all these, unfortunately, this is a possibility. So this is something that we may be in such an unfortunate situation where we have a combination of all these things which are giving us different pieces in different places. Or new physics. Of course, new physics is also a possible option because we have a coherent picture, we can have a coherent explanation of everything. This is really non-trivial. It could have been completely different. Different measurements could have been pointed toward different things, but this is not the case. We can have a coherent explanation of all these anomalies. So, at the end of the day, where are we? Is the nature teasing us, or is the nature teaching us? So, for this, we only have to wait for the next LHCb round of data to give us the verdict, to see what is the situation. I personally really hope that we are learning from nature and it's not just a joke. So I think the search for new physics looks very similar to this picture now. So this is where we, at least this is my personal feeling, this is where we are now. You see this map? This is the Toscanelli's map, which was used by Columbus. So just look at this, how wrong it is. I mean, it's really terribly, terribly wrong. We know that, but nevertheless, it served the purpose. So I hope we are in such a situation that even if we are wrong, but we are going for it and we are trying to learn and discover. So let's hope for some nice discoveries in the next few years. Thank you for your attention.
Okay. So thanks a lot, Nasila, for the very nice and complete talk. So now there is some time for questions and comments. So,
what kind of QCD improvements are you thinking about that could be necessary to do better analysis?
So, how can I explain this in words? It's very complicated. So basically, we have a hadronic part of the matrix element to calculate, and this hadronic part is very complicated. So we usually use QCD factorization for that, but not all of the ingredients are calculable in QCD factorization. So there are some parts that we cannot calculate in QCD factorization. And these are exactly the parts which are missing now, or we need more better approaches to deal with in order to decrease the uncertainties. But these uncertainties don't affect all the measurements or all the predictions. Like they affect angular observables and branch ratios, but not the ratios because they cancel in the ratios. But it's very complicated.
any other question?
So you didn't mention the anomalies in charge currents. What's your opinion about them?
Okay, so I was careful saying that I'm talking about FCNCs and ray decays, so they are not FCNCs and ray decays. But of course, there are also some deviations with the measurements in the charge currents. I don't know. I mean, the focus of this talk was not that, so this is the main reason that lack of time. My personal idea is that, okay, they are three-level diagrams, so it's a little bit more difficult to cook something really well motivated to explain those anomalies. And also I think that at the end of the day, if we try to explain really everything from all the different sectors at the same time, we can only be wrong, because by the time one of these anomalies in those sectors will go away. So I mean, being too enthusiastic is not always the best thing to do either. But this is my personal view.
Thanks.
Questions, comments? Okay, everything is clear. So if there are no more questions, so let's thank Nasila again.